realization result in a C0 sense for the very strong disorder regime for the directed polymer. So let me remind you of a few notations. So mu n, it's the endpoint distribution of our directed polymer, and mu n tilde, well, it's just the same thing, but ignoring the environment at the final time. And this thing, you can rewrite it as this thing. Okay, so for this reason, for instance, mu n infinity, well, okay, you have this inequality for free, and you can compare also LP norms if you want. So yeah, just say this thing is going to appear in the theorem, but you can replace it by mu n for free. Okay. So now, what the theorem? So it's due to comets Shiga and Yoshida in O3, but also there is an earlier version that was proved by Carmona and Hu in O2 for Gaussian environment. And what the theorem says is that if f beta is negative, then lim inf of the sum from n equal 1 to n. Okay, so let me write it like this. In over n. Okay, this is when n goes to infinity, is positive. And here I will define in as mu n 2, 2. Okay, so it's just a sum over arc x in ZD of mu n x square. Okay, so last time I gave you I stated some result, and there was no in in it. What appeared was, I think, the supremum norm of mu n. But if you look at it, these things are equivalent. Okay, because what you have, okay, is that in, okay, I guess it's yeah, in, okay, it's clearly larger than mu n infinity square. Okay, and it's clearly smaller than mu n infinity. Okay, for the second thing, okay, when you sum the squares, you just bound one of the two mu n x in the square by the infinite norm. Okay, and saying that either of the thing, okay, and this is smaller than 1. So saying that this goes to 0, it's the same thing as saying that the positive proportion is larger than delta for some delta. And then you see that saying that something is larger than delta, it's equivalent for all of these things. Okay, since your choice of delta is arbitrary. Okay, so this is well, the reason it's better to write the result in this form is that actually this result tells you a little bit more than that. But okay, in the end, this ends up to being the important consequence of the result. Also, the result gives you a comparison between this and f beta. Okay, these things are actually of the same order. Okay, with a proportionality coefficient, which also depends on beta. But so this is what will come out of the proof. Okay. So what is the proof? Well, what we know that 1 over n log wn converges. So what I'm going to try to do is to write wn as a sum and to make each term of the sum comparable to that. Okay. So log wm is really a sum because it's a sum from n equal 1 to n of log wn divided by wn minus 1. Okay, and the thing is that wn divided by wn minus 1, well, it's really 1 over wn minus 1 times the expectation of exponential sum of n equal 1 to k equal 1 to n minus 1 beta omega k xk minus lambda beta k, and then I have exponential beta omega n xn minus lambda beta, and yeah, then that's it. Okay, so now this thing here is the density of mu n minus 1 with respect to p. So this thing is nothing but e n minus 1 beta omega exponential beta omega n xn minus lambda beta. And I can rewrite it as, well, the sum over x in zd u n minus 1 x. And let me write this as zeta beta n x, where okay, zeta beta kz is equal to exponential beta omega kz minus lambda beta. Okay. Okay, so this is something that we want to use, but somehow what we want to use is the fact that yeah, the expectation of this with respect to this variable is, well, okay, we know that it cannot be positive from Jensen. Okay, the expectation, sorry, of the log of this, okay, with respect to this, you know that it's not positive, okay, due to Jensen, but you want to show that it's kind of really bounded away from 0 if the L infinity norm of this, okay, if In is positive. Okay, so we want to have, well, we want to have somehow this thing appearing. Okay, because we want to average with respect to that. This is how we will make In appear. Okay, so we write this as the sum from n equal 1 to n of, well, on one side I have log wn over wn minus 1 minus the expectation of log wn fn minus 1. Okay, so, and then I have a second term, which is the one I wanted at the beginning. Okay? Well, when you want something to appear, you just add it and you subtract it. Okay, and somehow, okay, so we have two terms. So let me call this an, and let me call this bn. Okay, so we know that when you divide this by n, okay, this converges to something negative. Bn is something that should be comparable to this. Okay, so what we want to make sure of is that an is not too big. Okay, and okay, what's nice about an is that it has a nice property actually. So what's the property satisfied by an as a sequence? Yeah, it's a martingale. Because when you want to make something a martingale, okay, any process when you want to make it a martingale, well, you just change the increments and you subtract the conditional expectation of the increment. Okay, this is called the double decomposition of a process. You can split, okay, any process indexed by integers into a part which is a martingale and a part which is progressively measurable. So it's not only adapted to the filtration, it's actually, I mean, like at the process at time n is measurable with respect to fn minus 1. Okay. So, yeah, so let's use this property. So, yeah, an, okay, first it's a martingale. It has a second nice property. Okay, what do we know about martingales? We don't know so much. So it has bounded increments. Okay? Why is it so? Well, you know that wn divided by wn minus 1. Okay, so yeah, it has bounded increment. Why? Because omega is bounded. Okay, and again, here I'm not making a big assumption. If you want to relax this assumption, it's just a matter of doing a bit of surgery. I think it's better to present first a clean proof, and then if you want to look at the modification, you can look at this paper. Okay, so wn over wn minus 1, well, if you look at the log of this, well, this is smaller than, well, yeah, this is smaller than 2 beta times n, okay? Okay, I mean, it's just that here you have an exponential in the end. Okay, so you have this exponential beta omega 1, 0 minus lambda beta. Okay, and this thing is smaller than 2 beta m. omega, okay, yeah, and xn. Okay, I mean, it's just, it's just this expression here, okay? Okay, so so far so good. So we can, okay, so if this is smaller than 2 beta m, okay, when you subtract, okay, actually this helps you, these three central things, but let's not worry about that, and let's say that the increment of an is smaller than 4 beta m, if you want. So an minus 1 is smaller than 4 beta n. Okay, so by assume as inequalities, what you have is that the probability that an is larger than n to the 3/4, well, this is smaller than exponential minus yes, I guess you have something like 32 beta m square and the n to the 1/2. Okay, this constant here is not important. Okay, the important thing is this. So you can use Borel-Cantelli, and you have that an divided by n goes to 0 almost surely. Okay, so all that remains to do is to show that Bn is comparable to this. Okay, and yeah, this is kind of this is not super difficult. So okay, let me define zeta beta bar, okay, which is zeta beta minus 1. Okay, just to make these variables centered. Okay. So here I'm summing these things. So I just want to show, okay, perhaps I can write this as a lemma. Okay. This is our assumption. Yeah, the lemma is the following. The expectation of mu and the sum of log wn fn. Okay, so there exists C1, C2 positive such that this is smaller than minus C2 in and it's larger than minus C1 in. Okay, and let's recall. In, it's the sum over x in ZD mu n x square. Okay. So I guess I should leave this on the board. So, and I will just use this now. So I will erase this part here. All good? Okay. So yes. let's go. So really, what we have, okay, Wn divided by Wn minus 1. If I take the log, is this here? Okay, what should we do? Okay, I will just open the door, see what's going on. So let's take back things where they were. So this thing, okay, we know that it's equal to mu n, sorry. Okay. So yeah, what I want to do is I want to rewrite it. Okay, so the function for which I know the Taylor expansion, okay, is log 1 plus x. Okay, so I'm just writing zeta beta as 1 plus zeta beta bar. Okay, and well, the good thing is that these things are centered, and the 1 it's going to go out because here I'm integrating against the probability. Okay, this is mu n x, mu tilde n x. Okay, so the good news is, yeah, when we are going to take the expectation, this thing can be considered as a constant. So what we are going to do now is use Taylor expansion. So what you have is that, well, if you look at log, okay, 1 plus u. Okay, so let's do a bit more than Taylor expansion because we want something, an inequality which is valid for every u. Okay, and well, this thing here, okay, you know that it's negative. And you know that the second derivative, well, it's bounded away from 0 on any compact. Okay, and because omega is bounded, okay, well, this thing has support which is bounded away from -1 and plus infinity. Okay, by compact I really mean, well, compact in -1 plus infinity. Okay, so you know that this thing, okay, well, let's put, well, minus C2 U2 U square and minus C1 U square. Okay. So let's call this Z, and you know that the expectation, okay, Z, yeah, of Z knowing Fn minus 1 is equal to 0. Okay, so now if you look at the expectation of log Z with respect, okay, with respect to Fn minus 1, it's bounded above by minus C2 In and bounded from below by minus C1. Sorry, I'm going a bit by the expectation of okay, so I'm just using this is 1 plus Z. Okay, so I'm just saying, okay, here I can just subtract Z. This won't change anything because of that. And then I'm using just this inequality. Okay. Okay, so this is for U in, yeah, exponential minus beta m minus lambda beta exponential beta m minus lambda beta. Okay, which is where Z lives. Okay. So now to conclude, I just need to show that the expectation of z square knowing fn minus 1, this is just in up to a constant. So yeah, this is what the expectation of. Yeah, so this is not. Yes, okay. So the expectation of. Yeah, so this is. Yeah, perhaps these things are C3, C4 because. Okay, so here I have, well, a sum, the square of a sum of centered variable, IID centered variable. Okay, the convex combination, Z is a convex combination of centered IID random variable. Okay, so when I'm expanding the square, only the diagonal terms are going to give me something. So what I get is the expectation of zeta beta 1 0 square, okay, times in, okay, times the sum over x in zd mu n x square. Okay, and well, this thing you can write it explicitly. It's just exponential lambda 2 beta minus 2 lambda beta minus 1. Okay, so here C1 and C2, they are just C3 and C4, but divided by this. Or multiplied by this, yes. Multiplied by this. Okay, so we have proved the lemma. So now I think we can conclude our proof. Any question about so far? So I'm just going to put everything together. So I have 1 over n log wn, which is larger than an over n. So this is plus or minus. So Bn, it's larger than minus C1, okay. Minus C1 sum from n equal 1 to n of In. Okay? Okay, so now I can take the limit on both sides. Okay? So what we get is that, well, f beta. Okay, so so let's take the lim sup on both sides. So the lim sup, it's larger. Okay, so here, well, this goes to 0, so this doesn't count. And this is larger. Okay, perhaps okay, it might be better to do it this way. So I'm sorry. 1 over n sum from n equal 1 to n In is larger than minus 1 over n log wn. Okay, plus an over C1n. Okay, and now you take the lim inf. So the lim inf here is larger than this limit plus this limit. And this is So you get that lim inf of 1 over n sum n equal 1 to n. My n is larger than minus f beta over c1 plus 0. Okay, so here the C1, okay, it depends on beta, but if you want this thing, it has quantitative value only if f beta is close to 0. So if you're close to beta C, basically you can say that, like if C1 is between, if beta is between beta C and beta C plus 1, basically, this thing is uniformly bounded, so perhaps it doesn't count. Okay, and this is sharp, okay, in the sense that, well, you have also a limit in the other direction. Okay, just have to replace things by C1 by C2, and you have a bound on the lim soup. Okay, so far, I think what we have proved is that the very strong disorder regime is non-empty, okay, provided that you don't have an atom, a too big atom on the essential supremum of your distribution. And we have proved that under very strong disorder assumption, well, you have endpoint localization in this sense. So now I think the next thing we want to prove is that in dimension 1 and 2, you have very strong disorder for every beta. Okay, because yeah, so far we have proved that in dimension 3, you have a weak disorder phase. We have proved that in the weak disorder, you converge to a Brownian motion, and you have no endpoint localization. In dimension, we have proved that for beta large, we have this very strong disorder phase. So now the only missing point really is this absence of phase transition in dimension 1 and 2. Okay, so okay, what we are going to do today is only about strong disorder, and we are going to see things about very strong disorder later on. Okay, so theorem. Okay, and by the same people, actually. When D equal 1, so Kometsu, Shiga, Yoshida, Carmona, and Hu, then W infinity equals 0 for every beta larger than 0. Okay, and yeah, the way we are going to prove this is actually not the way they've chosen to do it there. It's using, okay, the size by Ising perspective. So what's the idea? Well, you know that Wn beta, it's, a random variable which is non-negative and has expectation 1. So you can make it a probability density. Okay, you can define a probability on the environment which is such that the density with respect to the original IID distribution, it's just given by Wn. Okay, so now W infinity equals 0, it means that, and I'm going to put, well, okay, perhaps I should put it there. In the n goes to infinity limit, Pn and P becomes mutually singular. Okay? If this goes to 0, basically it means that asymptotically, when n grows, this measure starts to be carried by some increasingly small sets of omega. Okay? Okay, so that basically you can find two events, one that essentially supports this measure and one that essentially supports these measures, and the two are disjoint. Okay, so let's try to make this quantitative, and then when you prove this, basically, the idea is going to be to find these events, okay? Something which is typical for Pn and atypical for P, or vice versa. Okay. So, yeah, I'm going to state a lemma which is quantitative. Somehow to prove this, you don't need anything quantitative, but when we are going to be interested in very strong disorder later on, and this will come handy to have something quantitative to use. So what's the lemma? For any event A, so A is an event, concerning the environment. So I put F infinity. Of course, it doesn't make really sense to consider A outside of Fn because, and the result is that the expectation of the square root of W and beta. Okay, showing strong disorder is equivalent to showing that this goes to 0. This is smaller than the square root of PA plus the square root of Pn A complement. Okay? So basically what this means is that if you can find an event A, n, such that this is small and this is small, okay, so by small I just mean that this thing tends to 0, then you show that this thing tends to 0. Okay, so what I mean is that to prove this, we are going to show this. And we are going to find the ANs. Next objective, find AN such that P of AN goes to 0 and P n of ANC goes to 0. So the proof of this lemma, okay, well, it might look a bit exotic, but it's not. Okay, it's actually a pretty useful trick. So, okay. So you know that, well, by Jensen, this is smaller than this. And this does not give you much. So you can do something a bit better than that, basically. At the cost of losing a factor here, you can change the distribution with respect to which you are integrating. Okay, so let's write this down. Well, so it's very simple. So yeah, you can imagine, for instance, that G is a probability density. What I'm going to write is G, a positive function, but you just renormalize it if you want it to be a probability density. So this is a function of omega. Okay, and what I'm going to do is I'm just going to. Okay, and then you can use Cauchy-Schwarz. Okay, and then you say, okay, let's put a square here. This is smaller than the expectation of G omega Wn beta E G omega minus 1. This is just Cauchy-Schwarz, okay? I'm just saying this is a product of the square root of this times the square root of this. Okay, so this is true, okay, for any G, okay, from, yeah, I don't remember what omega is, but, yeah. G, positive. Okay, okay, for any G non-negative, but you don't want it to have to hit 0 with positive probability, because if not, the inequality is not very interesting. Okay, so what we are going to take here is to say, okay, let's take G, which is a constant on A and on A complement. Okay, so G is equal to the indicator of A plus alpha times the indicator of A complement. Okay, and then we are going to write this, optimize over alpha, okay, and see what it gives us. Okay, so and this thing here, it's nothing more than E G omega. Yeah, this is the probability density we're looking at. Okay, so yeah, what's this thing? So this thing, it's equal to 1, sorry, PA plus, okay, so it's P and A plus alpha, and then I have P and AC times and then I have PA plus alpha minus 1 P AC. Okay, and now I can, I can try to simplify my task a little bit. So here, okay, this thing is going to be interesting only if these things are small. Okay, so I just can consider that the other things are close to 1. Okay, that P of AC is close to 1, and P tilde N of A is close to 1. So this is smaller than 1 plus alpha Pn AC. Yeah, P of A plus alpha minus 1. Okay, and now basically the best choice of alpha will be when these two terms are proportional. So what I really want to do is I want to take alpha is equal to here I want to divide by the square root of this thing to get the square root. And here, okay, so let's see if this is the right thing. Pn of AC P of A. Okay, so now you get that the thing is equal to so what you get is 1 plus square root of Pn AC P of A. And then here you get P of A. Oh, yes, okay, alpha is equal to, sorry, this to the minus 1/2. Okay, and here you get square root of P of A, Pn AC. Okay, and here you have some simplification. So, okay, you can get P of A out here. Okay, and you get the square root of P of A, you can get it there. Okay, so you get square root of P of A plus square root of P and AC squared. Okay, and this is exactly what you wanted to get, because here, we have that the square is smaller than the square. Okay, so no, this optimization procedure is it's computation. So of course, I kind of take this out of my hat. Okay, but if you don't make this replacement by 1, it's a bit annoying to do. So this makes things a lot simpler, and But in fact, I think I never took the derivative with respect to alpha, so I'm not sure this is the optimal thing, but this kind of works for what we want to do. Okay, so now that we have this, okay, let's try to find these events, this sequence of event AN. Okay, so we want to find AN, which is typical under the tilted measure, okay, but atypical under the original one. And to guess what AN might be, we have to understand what this measure is. Okay? So let's try to do this. changes here. Okay, so this is dPn, and we can rewrite it as, well, you can just replace Wn by its expression. So you have 1 over 2d to the power n, sum over x in omega n, exponential sum from n equal 1 to n, beta omega n xn, minus lambda beta and then what do you want to do? Yes, that's it. Okay, you have the brackets here if you want, and then you have dp. And now you can look at this exponential thing here. This thing, well, it's a random variable and it has expectation 1, so it's a probability density. So you can just say that I just, by definition, okay, this thing is, by definition, dpx. Okay, px for x in omega n fixed, this is the probability whose density is equal to this. Okay, so what I can say is, well, when I sample something according to p tilde n, what I can do is just take an x uniformly at random on omega n, okay, and then sample something according to p tilde x. Okay, so now the question is, what is this measure? Okay, and the reason why we have taken this course is that somehow this expression here is nicer than Wn, because this thing is, a function which is a product of the omega n x's. Okay, so initially we had the product measure. Okay, so now if you take a measure whose density with respect to a product measure is a product of the marginals, then the new measure is also a product measure. Okay, so under px, omega n x are IID, no, R, n x are independent. Okay, and well, the probability that omega nx belongs to A. Okay, here A is a Borel set in R. The probability that omega nx belongs to A, well, it's equal to the probability that omega, it's equal to the probability that 1, 0 belongs to A under the original measure if x is not equal to xn or n strictly larger than n. And it's equal to, okay, perhaps this is case 1, and the case 2 is it's equal to well, the expectation of exponential beta omega 1, 0 minus lambda beta times the indicator of A. Okay, if n belongs to 1 n and x equal xn. Okay, so what p tilde x does with respect to the original measure is that it changes the distribution of the omegas along the graph of x. Okay? And what's important is that here, this thing is an increasing function of omega. Okay, so this change makes omegas bigger. Okay, this is just a consequence of this correlation inequality. Okay, so yeah, you can compute explicitly the expectation, and okay, so let's assume. Okay, we are going to assume that the omegas are centered. Okay, just because there is no loss of generality, you just have to add a constant to it. And you can compute, okay, these things, they have finite variance, and the expectation is lambda prime beta, which is larger than 0. So there is what we are going to do is really based on second moment computation, or perhaps, yeah, what we are using is concentration, but so for bounded variables or for exponentially integrable variables, there is no problem. I think everything will be more readable if we consider the Gaussian case. Okay, so special case. Gaussian. Okay, and here what we have is that under Px, what we have is that omega n x and x in dd is distributed like omega n x plus beta times the indicator that xn equal x and okay, n smaller than n under P. Okay, putting this density when you have a Gaussian, it's really just changing the mean of your Gaussian by beta. Okay, just making this computation explicit. Okay, 1 over square root of 2 pi integral exponential beta u. Lambda beta in the Gaussian case, it's beta square over 2. Okay. Exponential minus u squared over 2, indicator of A du. It's equal to, well, there is not much to do. I'm just saying this is just u minus beta squared. Okay, so you see that when you're adding this multiplicative factor, what you're doing is really you're changing the density from this to that, which is exactly shifting the mean. Okay. So So now let's combine this with this, and you get exactly what you get some representation for P, for what Pn is. So okay, and I will write it for Gaussian, okay. But everything that I say, okay, it's just a bit more annoying to write, but like all the computation that we are going to make, you can make them in the non-Gaussian case. Okay, so proposition. Okay, and this is a spine representation of pi n. And yeah, what is it? It's just that Pn that okay, so there is nothing to prove. We have already proved everything, okay? Yes. Like the distribution of this under Pn, it's just the expectation, okay, of the average of the distribution of this under P. Okay, so sampling something according to Pn is just, well, you sample a simple random walk, okay, and then you shift the values of your Gaussians along the path. Okay, and why spine representation? Well, okay, because this x along wings, you can consider this as some sort of backbone of your. Okay. Okay, so very good. So we are going to use this in order to try to look something, an event which is different under, that has very different probabilities under P and P tilde. Okay, so yes, let's do this, and let's start with dimension 1. Okay, and perhaps let's take a small break before doing that. I will just grab a coffee, and we'll be back in 1 second. Any question? Okay, so I just said offline, this spine representation is also valid when you have non-Gaussian environment. It's just that you have to write it in a different manner. Basically, instead of saying I am shifting the values of my variable along the spine, along the x that I've drawn that I've sampled like a simple random walk, what I'm doing is that I'm changing the distribution of the omegas along the spine. I'm replacing the original distribution by this distribution here, okay, where I basically added this exponential density. Okay, so basically this is called the exponential tilting of the distribution of the variable, and it turns out that for Gaussian, the exponential tilting is just adding a constant. And it makes things convenient. Okay, so let's try to look for some event AN. Okay, so yeah, I want to say under P tilde, the omegas are slightly bigger, okay, because I have added a constant to some of them. The problem is that I don't know exactly where the shifted things are. Okay, so because of course, like this is just an equality here, but like when I want to choose an event, I cannot base my event on what x is. Okay, simply because this makes no sense. Okay, so what I can do is, well, to try to just consider sites where x is likely to go. Okay, so, and so what I can do is to try to look at the average of omega on a box, okay, which is likely to contain x. Okay, all the graph of x. Okay, so what would be the box? Well, clearly, I just want to sum from 1 to n, okay, because beyond n, I'm not changing the environment anymore. And then okay, here I won't care about the parity, so half of the sites I'm considering, they have absolutely no chance of being modified, but this doesn't matter. This is just a factor 2 in my computation, and I don't worry about that. And I'm just going to take this smaller than n to the alpha, where alpha is strictly larger than 1/2. Okay? And then I will take the sum of the omega nx. Okay, so let's call this, I don't know, y, yn. Okay, so under P, yn is a centered Gaussian of variance well, okay. I will not do the integer roundings. Okay, so just consider that n to the alpha is an integer. And the variance is just a number of, this is, each of them are Gaussians of variance 1. Okay, again, variance 1 is not something special. You can just change the value of beta by a constant factor just to consider the general case. So it's a centered Gaussian of variance, okay, roughly n to the alpha plus 1. Okay, so this thing, it has fluctuations of the order n to the alpha plus 1/2. Okay, and under Pn, well, it's not a Gaussian anymore, but somehow it's close to being a Gaussian, because with very large probability, my x will remain in a box of diameter n to the alpha. Okay, just by like large deviation properties of concentration properties of the simple random walk. So under Pn, Yn is almost well, a Gaussian with the same variance and so here I'm taking d equal 1 and mean, and well, if everything in the if x is remaining in the box, it means that I have exactly n terms that have been shifted there. Okay, so the shift of the mean is n to the beta. Okay, the reason why it's not Gaussian, it's just because it's a Gaussian, but with a random shift of the mean. Okay, so it's a convolution of a Gaussian with the time spent by the random walk in the box. Okay, so well, somehow this seems quite good, because you see here. Well, you see that you can take, the only condition we have is that we have to take alpha larger than 1/2. So a priori, the fluctuation of my Gaussians around its mean, okay, the standard deviation of the Gaussian is much smaller than n. Okay? So you see that the distribution of Yn under P and under Pn, they are becoming increasingly singular when n grows. Okay, just because the difference of the mean is much larger than the standard deviation. Okay, so we are just going to try to exploit this. Okay, so you just you know, it's good, it's written. So an has to be the unlikely one. Okay, so an, okay, is going to be yes, an is going to be Yn is larger than beta n over 2. Okay, so an is unlikely under P and very likely under P tilde n. Let's compute. Okay, for the moment, if we want to prove that strong disorder holds, we are only interested in the fact that these things tend to 0. But I'm just going to I want to have something quantitative there, because I'm going to use it later on. So, well, the probability of an, which is the probability that Yn is larger than beta n over 2, well, it's smaller than exponential minus. Okay, you have a constant here. Do I want to care about that constant? Okay, let's put it there. So I think, let's put a 5, okay? Like, this 2n alpha plus 1, I guess you can say that this is smaller than 5 over 2n alpha. Okay, so here you have this 5, you have n alpha plus 1, and here you have beta square n square. Okay, okay. I'm just using the fact that the probability is that n is larger than u. I think this is smaller than exponential minus u squared over 2. Okay, this is true for u sufficiently large. Okay, and well, if you have a variance here, you just put the variance there. Okay, so yeah, here I get, in the end, exponential minus beta squared over 5 times n to the 1 minus alpha. Okay? And when I look at Pn of an, well, okay, I have two parts. So I have to really estimate the probability that the sum of these things is larger than beta n over 2. So either this thing is always equal to 1. Okay, either the walk spends all its time in the box, and the sum of these things is going to be equal to n beta, or it doesn't, and in that case, I'm just going to bound this probability by 1. Okay, so here I get this is smaller than P of, well, the probability that the max over n in 1n of xn is larger than n to the alpha, plus, well, the probability that yn, okay, and I have to put a complement here, that yn plus beta n is strictly smaller than beta n over 2. Okay, so this second term, okay, is exactly the same as the other one. Okay, so what I get is that P A N C is smaller than, okay, the probability that the walk goes past n to the alpha, it's really exponential minus some constant time n to the 2 alpha minus 1. Okay? Just think of Azuma's inequality. Okay? You're asking the sum of IID random variables to be much larger than square root of n. So this is, you get this u square over n, which is exactly this. Okay? I mean, you ask a sum of variables, you have less than big N variables, so this is always bigger. Okay. What you get is really n to the 2 alpha divided by n, and then you put some big N in front. Okay. And you don't care about it. You get, this can get absorbed in the exponential. Okay, so you get this plus exponential minus beta square over 5 times n to the 1 minus alpha. And we are good. Okay, this goes to 0, this goes to 0. So we have strong disorder for every beta in dimension 1. Okay, so let's try to do the same thing in dimension 2. Okay, and or in arbitrary dimension. Okay, you already know that it cannot work in dimension larger than 3 somehow. But okay, if you take d equal 2 here, Well, the problem here is that your sigma will be this. So sigma will be much larger than n. So your variables will not be different. And I mean, even if you take alpha equal to 1/2, okay, so that a decent portion of the work should remain in the box, well, it still doesn't do the job. So this, but it still doesn't do the job, but you're in the borderline case in dimension 2. Okay, in dimension 3, it looks very hopeless, okay, because if you put a 3 here, okay, you will get, even at 1/2, you get a power that is larger than 1, which is, it looks like a lost hope. In dimension 2, yes, it looks like if you take exactly alpha equal to 1/2, well, the distribution of the yn will be basically asymptotically different, but not going away, because the shift of one from another will be of order n times the random variable, okay, because this thing will well, it will be of order n, okay, if you take alpha equal to 1/2. So these variables, they will be, yeah, different from one another, but not becoming singular. So what one has to do is to change a little bit the strategy to be a bit more efficient. And a way to do that is, well, to be a bit more careful in what we do here. Okay? So in the sum we are considering here, what you really want to do is to give higher weights to sites that are more likely to be visited. Okay? So here we have given uniform weight in a box. But somehow, if you look at, I don't know if you, yeah, let's look at the set of, I won't draw a heat map because I don't know how to do that. But I can draw the set of points that have probability more than 1/2 of being visited. Okay, and okay, so this is okay. The set of okay, a set of points which is such that with probability 1/2 for each time. Okay, I'm sure that the graph of xn will fall here. So really, if you want to do this, what you will get is a paraboloid. Okay. Yeah, you have something like that, you know, for n sufficiently large. This is larger than 1/2. For alpha sufficiently large. Okay, so basically, yeah, perhaps we should sum around this. And you know, like the probability to be visited is 1 over square root of n. So we should take this into account. Like it really depends on n, so we should not take a uniform sum here. We should give higher weights to these guys close to the origin. Okay, so this is the idea. So yeah, let's try to do this. So okay, perhaps I can erase everything here and start with a new yn. Okay. So g larger than 2. And yeah, what do we want to consider? Okay, so yeah, I could consider some law of iterated logarithm, but this is not really necessary. So what I will do instead is something like that. I will consider yeah, no, okay. This is a simple thing. So yeah, I want to remain in the thing. Okay, so okay, let's try to do things with. And yes, what I want to take here is W and X. And okay, let's. Yeah, I think alpha n. Okay, and here I will put some. Okay, so you have alpha n here, and you have Fn there. Okay, so the idea is I want Fn to okay Fn. Okay, I want Fn to go to infinity so that I can make sure that my W will remain in the, my X will remain in that box, okay, with large probability. So I'm just taking this paraboloid, but I multiply it by a factor that depends on big N so that I'm sure that I won't go out. Okay, so, and here I want to make the sum dependent on little n. Okay, so what's the variance of yn? Okay, it's the same under P and Pn, okay, when we are going to consider like that under Pn you have a Gaussian plus this shift, and we are going to try to make this shift deterministic, okay, by making X stay in the box. Okay, so this variance here, it's n alpha n square okay, it's okay, so expectation of yn square, this is exactly this. Okay, I have, this is the number of terms that I have, this is the number of terms I have for a given time. Okay, let's do this and let's forget about the plus one. Okay. This is the number of terms I have for a given time. And this is the value of each term. Okay, so this is what I get. Is this correct? Yes. Oh, sorry. This is, sorry. We are in dimension 2. So what you get is alpha n square, and the number of terms is n times Fn square. Okay. Okay, and I don't care about constants. Okay. And now, if X remains in the box, the expectation of yn, okay, it's equal to, well, the sum from n equal 1 to n of Fn alpha n times n. Fn alpha n times beta. No, what yes. Okay. Most of this one side per unit of time is shifted, and it's shifted by beta. So this is what you get. Okay, so here you have some kind of minimax problem. You want to make this the biggest while you're making this the smallest. Okay, or Yeah, I want to maximize the shift for a constant variance. Okay?
You didn't understand why there's an F.
There isn't, yeah, because there is no F. Thank you. Okay, so the way you do this, okay, I mean, in the end, you don't need to check that this is optimal, but the best thing you can do is to make the ratio of these terms constant. Okay, so you need alpha n square and fn square to be proportional to alpha n. Okay, let's not. Okay, this thing is not going to be very important. We are going to choose it afterwards. We need just, we're going to take alpha n equal 1 over n. Okay, this is just because here we have some room to play with. Okay, so here the good thing is that this thing will give me log n times fn square. This will give me log n. Okay, so I'm good. Here I will have fluctuations that are over the square root of log n times fn. And here I will have a shift that is over the log n, which is much bigger than square root of log n, as you all know. So the important thing here is we need to take fn, which is much smaller than square root of log n. So yeah, I'm not really caring about optimization. So let's take fn equal to log n to the 1/4. Okay, and the law of iterated logarithm for the simple random walk really tells you that with large probability, we are staying in this paraboloid here. So let me write this as a lemma, and we will wrap up the proof from there. Okay, so what we have, okay. The probability that there exists n in 1n such that xn is larger than log n to the 1/4 times square root of n. Okay, this thing tends to 0. When n goes to infinity. Okay, are you willing to accept this? Okay, I mean, like, like you know that the upper envelope of this, it really behaves like square root of n log n. Okay, this is the law of iterated logarithm. So I'm just saying, well, okay, like this is always much bigger than this because. Okay, and the reason why I don't want to prove this is because this is a bit delicate because even though you have some margin with respect to law of iterated logarithm, you cannot do just a union bound. Okay, because you would get exponential minus log n to the 1/2, and then if you take a union bound with respect to n, well, you get n times exponential minus log n to the 1/2, and this diverges. Okay. Okay, so I think now we're good. We have that the probability that yn is larger than, okay, what are we going to take? Beta log n over 2, right? Okay. Well, this is smaller than exponential minus c beta log n. Okay. So c beta log n square divided by log n to the 3/2. Okay, so this is just because, I mean, here, okay, I'm wanting to deviate. Okay, I have a beta square here, and I guess, so yeah, this is, I want to deviate from log n. So really, this is from beta log n. So this is beta square log n squared divided by the variance, and the variance is really, yeah, log n times fn square. So, which is log n to the 3/2. Okay, so this is good. And on the other hand, I have that Pn Yn smaller than beta over 2. Sum n equal 1 to n alpha n. Okay, it's smaller than, well, the probability of, okay, let's call this, I don't know, an, which goes to 0, plus, and the second thing I get is the probability that yn plus sum plus beta sum from n equal 1 to n alpha n is smaller than beta over 2. Okay, so yeah, I'm just getting the same bound as before. Okay, this takes into account trajectories that goes out of the zone that was considered in the sum, and this takes into account trajectories that remain entirely inside. Okay, and therefore we have proved that very strong disorder holds in dimension 1. Strong disorder holds in dimension 1 and dimension 2, with a bit of a difference in the two statements. Okay, in dimension 1 we have shown that these things here, meaning also the expectation of the square root, decay like a stretch exponential. Okay, whereas the bound we have in dimension 2. Okay, I don't really care about this thing. This thing is actually, I think, well, okay, this thing is also not so good. So here and there, the bounds we have, they are not even polynomial in n. Okay, so for the moment this makes no difference, but when we try to prove very strong disorder, this is going to count. So what I want to do next week is to tell you about very strong disorder, how you prove it for every beta in dimension 1 and 2. Yeah, you will see that in dimension 1, basically, the statement follows almost directly from what we have proved here. And you will see why in dimension 2 we need to do something more. Any question? Okay, so I'll see you on Tuesday.